Hello, and welcome to a presentation about making decisions when you're faced with solving engineering problems, a lot like homework problems. So let's go ahead and get started. So I've tried to depict representative examples of what you're faced with in thermodynamics class when you read a homework problem and then you say, okay, now what? Well, one reason that I think that thermodynamics could be classified as a difficult topic, difficult subject, difficult class is that when you're faced with an engineering problem, you have to make some decisions. And so I've depicted here in the bottom right, in many cases, you have to make decision after decision after decision. Over here on the left, here's a student who's one of those decisions is, how do I model my substance? Do I have an ideal gas or do I have a phase change substance? And I'm going to try to summarize in this video some tips about making decisions both within your class and as a practicing engineer on how do you make certain engineering decisions in order to solve a problem. So here's the roadmap that I want to cover. And first is once you've read your problem, you've got to decide, it's almost like step zero, even before with a sketch. Do I have an open system or a closed system? And quickly we'll review in your mind, does the continuity equation come to your mind? Does the first law of thermodynamics come to your mind once you've decided open system or closed system? Next decision that you're faced with is, what substance am I dealing with? Do I have a phase change substance, or do I have an ideal gas, or do I have something else? Those are the decisions you have to make. Now, let's say you've decided, yeah, I've got an ideal gas here. My problem is going to relate to an ideal gas substance. After that, you have to decide as an engineer, am I going to treat the specific heat of the ideal gas as a constant or a variable? And that can be a tough decision. And you're going to be looking towards your instructor or professor when you're in class on helping you with that decision. But when you're an engineer in practice, you don't have that professor to look over your shoulder. So I'll try to give you some advice there. And then finally, I'll tell you, as folks get into chapter 6 relating to problem solving that involves the second law of thermodynamics and evaluating entropy changes, the property entropy, calculating S2 minus S1, want to give you some decision-making guidance on calculating entropy change as well. And that'll help get you up to speed. Okay, so you've read an engineering problem. The first thing you've got to decide is, do I have a closed system or an open system? And what you detect here is, do I have mass flowing into or out of my control surface that I've selected? My problem at hand, I'm thinking about a control surface. Do I have mass flowing in and or out? If I do, then it's an open system. If not, if it's a fixed mass, it's a closed system. Okay. So how about the continuity equation for a closed system? In your mind, you say, okay, I think I've got this. Here's an example of a closed system would be a gas or a substance contained within a piston and cylinder. The control volume could also be a brick or a glass of water. But in any event, when you're studying the process, the mass is fixed, the mass is constant, and the continuity equation then for a closed system would be M1 equals M2. A little more complex for an open system. And for this situation, I've said, let's say we've got an open system that's operating in a steady state, steady flow manner with only one inlet and one outlet. Many of your problems are this category of problems. And so, for example, the statement of continuity for open system, steady state, steady flow, one inlet, one outlet is simply m.1 equals m.2. The rate of mass flow coming in, that's m.1, exactly equals the mass flow rate leaving m.2. quick refresher on the first law of thermodynamics. Let's say you have a closed system. I hope you have this in your head without needing to go to a formula sheet. What's the statement of the first law for a closed system? Statement is the left-hand side, energy transfer terms, Q in minus W out equals right-hand side, energy change terms, the internal energy change plus the kinetic energy change plus the potential energy change plus any other energy changes that are involved. All right. Well, then now let's look at the statement of the first law of thermodynamics for an open system, but for that special case where we have steady state, steady flow with only one inlet and one outlet. Large proportion of your engineering problems are this category. Left-hand side of the first law. Well, energy transfer terms at the boundaries, Q dot in minus W dot out, the rate of heat transfer in, the rate of heat transfer out. The right-hand side of the first law, well, it's M dot times a big bunch of bracket terms. Well, little different than the closed system. There's an enthalpy change term, H2 minus H1, to account for flow work, plus a kinetic energy term and a potential energy term. And so, wow, when you put it on paper, it really looks pretty easy, but it's up to you. You've got to make those engineering decisions on, do I have an open system or a closed system? And then pull out of your head statements of the continuity equation, statements of the first law. The next thing we have to do as an engineer is select the model for our substance. What kind of substance do we have? And I tried to summarize the weeks and weeks of work you've done so far in this class, and I've tried to summarize it in terms of a pressure-specific volume diagram, and I've drawn in the tried and true vapor dome, the vapor dome, okay? And I've tried to color code the ways to help you make decisions. When I'm under the dome, I've got a phase change substance. There's no doubt about it. When I'm under the dome, I've got a saturated mixture of a liquid and a vapor. And so my model is definitely phase change substance. Let's look over here to the left of the vapor dome. When you're to the left of the vapor dome, you've got an incompressible liquid, and that's your substance model there. And we'll talk at the end a little bit about how you would get properties for an incompressible substance. Now, the trick has to do with when you're outside the vapor dome, what types of substance models do you select? If you're way removed from the vapor dome, let's say when the T over T critical is greater than 5 and P over P critical is less than 1. In other words, lower than critical pressures and higher than critical temperatures, then you've got an ideal gas. And that's why I've shown this as green. Green, ideal gas model. I'm going to proceed ahead. Now, the yellow clouds. The yellow clouds, when you are close to the vapor dome, that's where I've labeled it. Check Z, check the compressibility factor. I got to tell you that in most of your engineering problems, you're not faced with this decision. So it's really pretty unusual. It would only be situations where you're dealing with cryogenic substances, in other words, very, very cold substances, or extremely high pressure substances, that you're going to have to check Z. Now, notice here I've changed. Look, over here in red, there are many times when you are very close to the vapor dome, when you have steam, when you recognize, or refrigerant, where you recognize in your head that you have a substance that's going to be a phase change substance. That's a no-brainer. You don't have to check Z for situations like that. You say, look, I've got a phase change substance, and that's why I've sneaked in the cloud that's red and sort of also a cloud that's kind of orange that's in Never Never Land. So certainly there are times where, as an engineer, you do not need to check Z. Okay, so green, ideal gas model, red, phase change model. Okay, so now decision trees. Let's look at a very simple substance modeling decision tree. First question you ask yourself as engineer, is the substance commonly regarded as a gas? In your head, from freshman chemistry, do you recognize the substance as a gas? If yes, you're going to come over to this way. If no, then they're in that red box. You've got a phase change substance, and you may recognize it as a commonly recognized phase change substance like H2O, refrigerant, and propane. That's where you're going to use the property tables for all your properties, particularly U, internal energy, H, enthalpy, and S, entropy. Okay, decision tree over to the right. Yes, I've got a gas. Did you have a situation where you quickly checked Z? You don't need to spend a lot of time on it, but did you quickly check Z and see, look, Z is nearly 1.0. If yes, if the compressibility factor Z is nearly 1.0, then you're green, you're good to go. Ideal gas model, PV is equal to RT, or little v is equal to RT over P. And you know all those combinations of the ideal gas equation of state. If Z is not 1.0, then you're yellow, and you're you're limited in your engineering analyses. You're going to say P times little v is equal to ZRT. That's the real gas equation of state. Very similar equation of state. Or little v is equal to ZRT over P. And look, in this class, a small proportion of our problems are associated with the compressibility factor and real gases. Most of the time in this class and in the engineering world, you're dealing either with phase change substances or ideal gases. Next decision tree. Ideal gas, let's say we have an ideal gas. We've got a decision tree on modeling the specific heat of the ideal gas. So let's go over this decision tree. Do I have an ideal gas? Yes, we'll take the left-hand fork. If no, we'll use property tables, H2O, steam. All right, yes, I have an ideal gas. Can I treat specific heat, in other words, C sub P and or C sub V, can I treat it as a constant? If the answer is yes, we'll go down this road. If yes, constant specific heat. Maybe I'm directed to treat the ideal gas as a constant specific heat. I'll go down this road. Or I may do a little studying or see that in many cases, the temperature change of a process is a small temperature change. That entitles me for an ideal gas to say I've got constant specific heat. So what do? Yes, constant specific heat. You will select CP or CV at a representative temperature from table A20, or it may be given in your problem statement. And that's, so what? So what? Well, so what? If CP or CV is a constant, then you immediately jump down to remembering that internal energy change, delta U, is C sub V, constant, times delta T, and enthalpy change, H2 minus H1, is CP, constant, times delta T. So, man, this is a very easy modeling approach to do your math. Okay, back here. I have to treat my specific heat as a variable. In other words, no, not constant. Now, the next question you ask, I can't have constant specific heat. Do I have the substance air? The substance air, is that given? If yes, what do? We go to table A22 and look up either H or U at the temperature of the substance. Really very easy. It's a lookup exercise. And then when we're analyzing a problem, then we're going to determine delta U or delta H, and the units will be kilojoules per kilogram. Okay. Do I have the substance air? No, I don't have the substance air, but I've got an ideal gas. Okay. Then you'll go to table A23, look up U or H at the different states' temperatures in order to determine delta U or delta H. But for those of you that are familiar with table A23, remember that you've got to watch molar units in table A23, and I'm going to give you a little look at that a little later. But remember, table A22, table A23, you're going to have to divide those U bar and H bar values by the molecular weight of your substance to get U or H. Now, let's say you're interested in more details. You can go to my YouTube video, Ideal Gas 03, and really dive down into more and more details about ideal gases with either constant or variable specific heats. Okay, the next topic is going to be so important for you as you get into chapter 6 of your textbook, and you're having to determine entropy changes S2 minus S1. So remember, what is entropy? Well, entropy is a property, little s, and think of a small value of S would be a substance that would be highly ordered, like I've tried to depict here, S1, highly ordered, a lower value of S, compared to state 2, where I've got more disorder. S2 would be a higher value. So what's the difference between entropy change, S2 minus S1, and entropy production, sigma? That confounded me for a good long time until I dug down and got a much better understanding of those two different categories. Okay. Entropy is a property. S, it's a property similar to internal energy, enthalpy, pressure, temperature, specific volume. All those are intensive properties. Entropy production, sigma, depends both on the property changes of the substance and the heat transfer across the system boundary. So that's the way I remember the difference between entropy change, S2 minus S1, and sigma, the entropy production. Notice here how I haven't said sigma 2 and sigma 1. Sigma depends on the property change and the process that involves heat transfer. Okay, so you can learn more about entropy production, sigma, and entropy change if you go to my YouTube video about entropy production for closed systems. So if you can chase that down, that'll give you a fuller understanding with worked out examples about those. But for this presentation, let's just move ahead. Okay. So this is entropy change starting point. So my job, let's say in chapter 6, I'm asked over and over, calculate the entropy change S2 minus S1. And a lot of times that goes into needing to calculate entropy production sigma, but the first step is calculate S2 minus S1. Many students have tough time with this, and I'm trying to give you some starter tips on how to get started. And look, Dr. Von Spakovsky does a superb job, along with the other instructors, starting with the TDS equations that are given in your book. Now, these can be derived, but let's start with these TDS equations, and I'm going to suggest that you can derive expressions for S2 minus S1 from these two expressions. For this presentation, let's look at the second TDS equation. It's a differential equation that involves 1, 2, 3, 4, 5. I had to count them, properties. TDS, it's a differential equation. TDS is equal to DH minus V dP. All right. I want to walk you through how you can derive expressions for S2 minus S1 starting there. Let's divide both sides by T to give us, on the second relation, ds is equal to dH over T minus V over T dP. Let's work only on ideal gases. So notice the top label, title of this slide, ideal gas entropy change. Ideal gas entropy change. How can we simplify this differential equation for ideal gas? Well, dH is Cp dt. Okay, dH is Cp dt. So remember, I've got this T in the divisor here. Next term, V over T. For an ideal gas, V over T is just R over P. That's the ideal gas equation of state. I'm getting in better shape here. Do you see? So that's from ideal gas fundamentals. ds is Cp divided by T. dt minus r over p dp. Now let's integrate both sides. Left-hand side, very easy. The integral of ds is just s evaluated from 1 to 2. So we've got s2 minus s1, left-hand side. Right-hand side, first term, cp divided by t dt. Wow. Wow. If CP is constant, we've got it made, don't we? If CP is not constant, we're stuck with this expression, the integral from T1 to T2 of CP dt divided by T. That can be complex. Let's integrate the second term, minus R over P dP. That's easy. R is a constant, minus R, integral of dP divided by P is natural log. So we've got minus R log P2 over P1. So let's see, how can we simplify? Here we go. We've got S2 minus S1 equals question mark minus R log P2 over P1. Question mark. Uh-oh. We have to make that decision. Go to our decision. Is CP constant or is it variable? And I want to work you through both situations. Once you've made your decision, or if you've gotten direction from your professor about, I want you to hold CP constant, or I want you to treat CP as a variable. Okay, you see that, look at this decision tree. If CP is constant, we've got to remember where we left off. We've got question mark here. If CP is constant, I've got an easy integral. Look at this. As we go down this left-hand branch, CP is a constant. I'll pull it out of the integral, integrate dt over t, which is natural log of t from state 1 to state 2. So I've got my final result for CP constant, ideal gas. S2 minus S1 is this expression that you can fish out from your book. But do you see that you can derive it? It's not just a formula. S2 minus S1 is CP, natural log T2 over T1 minus R, natural log P2 over P1. Easy, simple calculator work. Okay, right-hand side where CP is a variable. Notice here in your textbook, what it does is it does this integration, and now it says it's two numbers. This integral, this complex integral is evaluated and it reduces to two numbers minus R log P2 over P1. You see that? Okay, see, here's the, so this complex integral reduces to the difference between two numbers. A little bit more on that in a second. Minus R log P2 over P1. We must not forget this term, and so many students forget that. And they lose so much credit on quizzes and tests when they forget that term. So it remains for us to look up in tables values for S02 and S01. Okay, so these are going to be lookup values in tables. S02 minus S01. Okay, and so these are called, these S0 terms are called the zero pressure entropy values, and they're looked up in tables. Okay, so you still with me? We've got equation 620 that we derived for an ideal gas with variable specific heat. To calculate S2 minus S1, we've got three things to worry about. S02 minus S01 minus R natural log P2 over P1. Be very aware of that. Now, back to decision trees. Do we have the substance air? If we have the substance air, we go to table A22 and look up S02 and S01. Easy. If we do not have air, and we've got CO2 or carbon monoxide or pure nitrogen, we've got to go to table A23 and ultimately look up and determine S02 and S01, but there's a trick there. So let's look at the tricks. Okay, table A20. This details for getting S2 minus S1. Let's look at the situation first where CP is a constant. Where CP is constant, we're looking for this evaluation. S2 minus S1 is CP natural log T2 over T1 minus R log P2 over P1. How did I get R? R bar over the molecular weight for the ideal gas. Where do I get CP, which is constant? I go to table A20. I look up my substance, and I must select a value for CP at a representative temperature that's representative of the process that you're analyzing. Okay. CP is constant, but I don't have anything tabulated here. For monatomic gases, which are helium, neon, and argon, then you have to do some digging in table A21 to see that, well, R is R bar over the molecular weight. And also you see that for these three monatomic gases, CP is simply 5/2 R, or in other words, 2.5 times R. That's the nature of a monatomic gas. So scientists can predict analytically the values for CP for monatomic gases. So if you have a monatomic gas, recognize you got to go to table A21 to refresh your memory that for monatomic ideal gases, CP is 2.5 times R. Okay, the next type of specific heat, S2 minus S1, and let's see, what have I got here? Variable specific heat for air, So I've got the substance air. I will go to table A22. I'm looking for S02 and S01. In other words, I've got two temperatures. So for example, if my temperatures were 300 and 500 degrees K, I simply look up and write down values for S0, and I look at my units, kilojoules per kilogram degree K. That's the way you get S0 values for air. I'm going to repeat myself again. Remember, to get S2 minus S1 for air, it's S02 minus S01 minus natural log P2 over P1. Let's move on to, let's say we have an ideal gas, variable specific heat, but darn it, it's not air. It's carbon dioxide or carbon monoxide or nitrogen. Okay, so then we will go to get our S0 terms. We go to table A23, but notice carefully, if you look at this slide carefully, notice how there's bars over top of H, U, and S. It's S0 bar, H bar. Okay. That means it's molar units. So you study quickly, see that for S0 bar units, kilojoules per kilomole degree K. And so very important that once you've written down your numbers for your S0 numbers, you've got to divide by the molecular weight to get your S0 units in terms of kilojoules per kilogram degree K. Yet another detail that a lot of students overlook. But again, don't forget, let's look back up at this slide, to calculate S2 minus S1 for your substance, you've got the S0 terms minus R natural log P2 over P1. I hope that that gives you some tips on how to do well and perform well for Chapter 6 problems. I've got one last topic to cover to complete this presentation, is evaluating properties when your substance is a compressed liquid. In other words, it's a phase change substance. It's to the left of the vapor dome. It's a compressed liquid, kind of like shower water or a bucket full of water or river water. Well, all of these examples are at a temperature below the boiling point, and all of these are at 1 atmosphere pressure, aren't they? They're all below the boiling point at 100 kPa. That's why they're compressed liquids. And so the reminder is to go back to Chapter 3 to refresh your memory, to see that properties for compressed liquids depend only on the incompressible fluid temperature. They depend on the temperature only. So the next slide summarizes that to bring it home. Key conclusion for compressed liquid substances. So in other words, in the blue, to the left of the dome, use your temperature table to look up V as V sub F at temperature. U is U sub F at your temperature. H sub F at your temperature, or S is S sub F at your temperature. So here's a reprise of your temperature table for water. Okay. And so just get in your head, if I've got a temperature, if my tap water is at 23 degrees C, I'm going to look up all these properties at the F, at the saturated liquid condition at the temperature of the fluid. Okay, so we're at the end. So let's see what we covered on our decision trees. You've got to understand your fundamentals first. Closed system or open system? Do you know in your head the continuity equation, the first law of thermodynamics, and the second law, which says entropy production must be greater than or equal to 0? Also, decision trees related to determining your substance. Once you've determined your substance and it's an ideal gas, is specific heat constant or is it variable? Well, that kind of gets us up to speed. I hope that this set of tips is going to help you in your Chapter 6 performance. In other words, reading a problem, making decisions after you've read the words of the problem, closed system or open system. What's my substance? Do I have an ideal gas or a phase change substance? If I have an ideal gas, do I treat it as constant specific heat or variable specific heat? And that covers it. Best of luck as you continue to improve your problem-solving skills.